we can go ahead and get started. So today all I really wanted to do was go through section 2. If I have time at the end, I might go through some examples from the last section if you guys want, or if you have specific questions about the homework, I can work through some of those if you would like to, but I'll just start with section 2. So section 2 is basically just only on addition. So the first type of addition we learned about was addition of HX to alkenes. That's a hydrogen and a halogen. So how this reaction works is you have an alkene, okay? You have a double bond, and we know the double bond is nucleophilic because we have this pi bond. So it can donate an electron pair from this pi bond, okay? And then this HX bond is polar, so hydrogen will be electrophilic, which means it'll be partially positively charged in this compound. And then when this X comes off as an anion, it will be nucleophilic. Okay. So addition of HX to alkenes, it's literally just the opposite of dehydro. That's supposed to say dehydro, but dehydrohalogenation, like we learned last section, is just the opposite of that. So instead of taking off a hydrogen and a halogen, you're just putting them back on. So just try to remember that. So here's the general equation. You start with an alkene. Like I said, this pi bond is nucleophilic, so it'll be able to donate electrons to this hydrogen from the HX. That HX bond will break, and X can be any halogen, by the way. So this HX bond will break. These HX bonding electrons will go to the X, okay? So, and we'll get to regiochemistry in a minute, but you know that the hydrogen adds to the carbon with the most hydrogens already on it. In this case, it doesn't matter because they have the same number of hydrogens. So hydrogen will add to one of them. In this case, it added to this carbon right here. So we added this hydrogen to this carbon, and then a positive charge forms in the other one. So you always form a carbocation, and then the anion from the HX will attack that positively charged carbon there. And then you have your product. Okay. Makes sense? Okay. And then also, I've written up here, don't forget about rearrangement. So from now on, after the last section, literally anytime you see a carbocation, you have to consider if it can rearrange. Okay, so he won't specifically tell you it'll rearrange. Okay, but anytime you see a carbocation, you have to consider if it will. So just remember that a carbocation can rearrange if there's an adjacent hydrogen or methyl group that can switch places with the positive charge to make a more stable carbocation. Okay, so just always remember to look out for that. In this case, I can't move anything to make a more stable one. Okay, so if it's just a straight chain, you can't rearrange because it's just a straight chain. So no matter where you put this, it'll either be primary or secondary. So again, this is a product here. You just added the hydrogen to one carbon, and you added to the halogen to the other doubly bonded carbon. Okay, so where's the pen? So these addition reactions have regiochemistry. And regiochemistry, remember, is studying the distribution of the different structural isomers, as which one is the major product. And structural isomers have the same formula but different connectivity. Okay, so regiochemistry of addition of HX to alkenes is determined by the stability of the carbocation. Okay, so it follows Markov-Nikov's rule, which says that in addition of HX to an alkene, the hydrogen will add to the doubly bonded carbon with the most amount of hydrogens on it. Okay, and basically, if you can't remember, like specifically what Markov-Nikov's rule is, all Markov-Nikov's rule is just make the most stable carbocation you can. Okay. So, I have an example here. Okay. So with this alkene here, I could either put the hydrogen here with the methyl group, and then the bromine here, or I could put the bromine here and the hydrogen here. Okay. So we can write down the mechanism to see what the major product will be. So again, you always start this reaction with the arrow coming from the double bond to the hydrogen, okay, because this double bond is nucleophilic, hydrogen is electrophilic. So there it goes from the double bond to the hydrogen. Okay, this HBr bond breaks, and those bonding electrons go to the bromine. Okay, so here, this carbon here has no hydrogens on it, right? Because it has this methyl group. This carbon here has one, oh, for Pete's sake, has one hydrogen already on it. Okay, so according to Markov-Nikov's rule, we'll add the hydrogen to this carbon because it already has the most hydrogens. Okay. Okay, so when I do that, I form a positive charge on this carbon here. Okay, and if I added the hydrogen to this top carbon here instead of this one, then the positive charge would form on this carbon, and that would give me a secondary carbocation with the positive charge here rather than a tertiary up here. Okay, so all the Markov-Nikov's rule is telling you is this, that whether there's an option to make like a secondary or tertiary carbocation, you'll always make the more stable one. Okay, so finish this out. Okay, so we have that bromine anion that we got from this HBr when that bond broke. Okay, and those lone pair electrons will just attack on that positively charged carbon, and I'll form that product. And this will be our major product.
Okay, so we did a rearrangement here or not?
No, so rearrangement only happens when there's a carbocation already present. Markov-Nikov's rule is you're not making a carbocation and then switching it around to make a more stable one. You're just making the more stable one to begin with. Does that make sense?
Yeah.
But the driving force is still the same, that you just want the most stable carbocation that you can make. Be good with this one? Any other questions?
But it's not wrong if we write out both hydrogens at the bottom, though, is it?
What do you mean?
In the final product?
Oh, like here?
Yeah, at the bottom.
Like that?
Yeah.
No, it's not wrong.
Yeah, I don't have a problem with that.
Gotcha. You don't always have to show, like, especially in line structures, if nothing's there, then you're already assuming that the carbon has hydrogens on it. If you'll remember way back in the first semester, you always just assume that all the carbons have 4 bonds and they have hydrogens if nothing else is shown. Okay, so if I didn't have anything there, it would still be right. And that's probably what you'll see most of the time. I just put the hydrogens there for clarity's sake, but that is really your product. Because all of these carbons have 2 hydrogens on it, but you don't have to show them. Okay.
Does he always want us to write the major, or can we write both the major and the minor?
So he will tell you, most likely. He'll either ask you for the major product and ask you like for the mechanism of the major product, or he'll ask you for like all the possible products, and then maybe it'll ask you what the
Okay.
major one is. Okay. So just like, so we already had radiochemistry. Addition of HX also has stereochemistry. And if you remember the difference between radiochemistry and stereochemistry is studying the distribution of different stereoisomers as product, and stereoisomers have the same formula, same connectivity, but different geometries. Okay, so in this case, don't write this down yet because I messed it up and I forgot to go back and change it. One moment. Okay, so that, what I just drew is an isopropyl group, if you remember what that looks like. Sorry about that. Okay, so stereochemistry is also determined by the structure of the carbocation. If the intermediate carbocation is prochiral, the product of addition of HX will be a racemic mixture. A racemic mixture is an even mix of two different configurations. So like you'll have 50% S configuration, 50% R. And prochiral is telling you that when you make the carbocation, if it has 3 different groups on it, and it's prochiral, because you can make a chiral compound out of that. And remember, chiral means you have 4 different groups connected to it.
Prochiral is 4 different groups.
So prochiral, a prochiral carbocation, it's telling you that the carbocation has 3 different groups on it. Okay, because it can make a chiral compound with 4 different groups on it. Okay. Does that make sense? Okay. So if the carbocation is prochiral, then the product will be a racemic mixture. Yeah, so this is saying prochiral means that carbocation has 3 different groups on it. So an example of this, we have, okay, we have our doubly bonded carbons here. This carbon has a methyl group and a hydrogen on it. This one has a methyl group and a isopropyl group on it. Okay, so it works the same way. The arrow goes from the double bond to the hydrogen. This HCl bond will break. Those bonding electrons will go to the chlorine. Okay, and then the hydrogen will add to the carbon that already has most hydrogen. So this has radiochemistry and stereochemistry. The hydrogen will add to this carbon because it already has 1 hydrogen. Okay, and the positive charge will form on this one. Okay, so this carbocation, I have this group here, which this is just a methyl group, right? So I have CH2 to CH3, or an ethyl group, sorry. So that's why I messed up there, because I didn't realize it until after I heard the whole problem, that this is also an ethyl group, so it has to be different. But yeah, this is just an ethyl group. Don't let wedges and things mess you up. And we have a methyl group here, and then an isopropyl group up here. Okay, so this carbocation, this carbon here with the positive charge, has 3 different groups attached to it. So that means it's this prochiral. Okay, so we know our product will be a racemic mixture. Okay, so now that chlorine anion or nucleophile can attack a positively charged carbon. Okay, and a racemic mixture, it comes from this carbocation where this chlorine has an equal chance of attacking from the top or from the bottom. So half your product will occur from this chlorine attacking from the top here, and half of it will occur from the chlorine attacking from the bottom down here. Okay, so I worked this out. I don't remember which one is R and which one is S. If you guys want to review that, I can go through that right now. I don't think you'll have to do that on test, but There's a slight chance. I really don't think you'll have to, but if you want me to, I can go through how to figure out if it's R or S. But if not, I'm good if you're good.
It's probably not gonna be on the test, I think.
Yeah, I don't think it will.
I wouldn't mind knowing how though, sorry.
Okay, I'll pull up
Just
another.
because, I mean, I think I know how,
Yeah.
so if you wanna wait, just do that tomorrow with me, it's fine. They don't wanna do it.
Okay, yeah, remind me tomorrow and I'll do it with you. Okay, but it's just the like assign priorities, make sure the lowest priority is the back, rotate, blah, blah, blah.
Put down the lowest bond.
Yeah. So basically the takeaway is that half of this chiral carbon is in, I think this one is in S. And I think this one is in R. I don't remember, I could be wrong. But just half and half is in S and R. Okay, that's what a racemic mixture is. So if your carbocation is prochiral, you'll have a racemic mixture. Okay, and you don't have to write out both of the products. When you have a racemic mixture, you can, let me get an eraser. Because you won't always have, you won't always know what's in the front and in the back with the substrate, so you can't tell what's where. But even then, even if you don't have like the wedges and the dotted lines, if there's still 3 groups attached to the carbocation, then it's still prochiral and it'll still be racemic. But instead of like doing all this line and wedge stuff, you can just do
I think the complicated part is rotation.
so this isn't the rotation thing.
Okay.
Rotation is only in, 1 second. So you don't have to write out like the wedges and the things. You can just say this and just put that it's racemic because that implies that you have half and half in RNS. So the rotation, that is only in E2 reactions. That's where when it has to be anticoplanar, and if it's not, then you have to rotate it like 60 degrees. So there's no rotation in addition. Does that make sense? The only like rotation that I mentioned before is when you're trying to figure out absolute configuration, so R and S, when you have to put the lowest group in the back, and then R is if groups 1, 2, 3 are going clockwise, S configuration is when groups 1, 2, 3 is going counterclockwise. You remember that?
Yeah.
Okay.
Okay.
Yeah, I don't think you'll have to do that, but yeah, it's a different rotation. Okay, so we're not doing like this 60 degrees thing. Okay, any more questions on this one before I move on? Okay. Okay, so the other type of hydration or addition reaction we learned is hydration, which is where we add water to an alkene, which forms an alcohol. And if you remember from last section, this is just the opposite of dehydration of alcohols, where we take off a hydrogen and the OH group to form an alkene. This is just the backwards, where we add water to the alkene to make an alcohol. Okay, so this mechanism is pretty much the same. There's like 2 extra steps just because of that OH not being a good leaving group. So there are just a few extra things we have to do that, but the mechanism in general is the same. So you start with your alkene. Yes.
On the mechanism, it doesn't really show the protonation of sulfuric acid to the water to
Right.
H3 plus.
Right. Yeah. So when you have something catalyzed by an acid, you can either write that you have like the full acid if you need to like in dehydration when we had to use the anion of sulfuric acid. You remember when we did that? That should be a 3. Well, there was a part where we had to use the anion of sulfuric acid. So if you're using like the other part of your acid, then you need to write the whole thing. But if you don't, you can write hydronium, which
Okay.
that's what you get when you dissolve acid in water, is
Okay.
hydronium, okay? Or you can just write H+, okay? They all just mean that it's catalyzed by acid. It just depends on what you need it for, if that makes sense. So in like second semester, you won't have to, or at least Dr. Sun won't like explicitly show protonation. You might sometimes, but, or like the actual arrows of it. But yeah, it just works the same way whether you have hydronium, H+, or actual like sulfuric acid. You following me?
Yeah.
Okay. So here we have our alkene, and this is just saying we have water, we have sulfuric acid, and down here it's just H3O+. There should be a positive charge there. Okay, so we start with our alkene. And again, the arrow goes from the double bond to the hydrogen. It works pretty much the exact same way, but you have to protonate this water to hydronium before you can do this, okay? Or water doesn't break apart very easily unless that OH group is protonated. So it works about the same way as like in dehydration when you had to protonate the OH group before you can take it off. It's the same thing here. You have to protonate this OH group before you can separate this, okay? So the arrow goes from the double bond to the hydrogen. This OH bond will break, and the bonding electrons will go to the oxygen, which will neutralize that positive charge, okay? And then we reform water here, okay? So again, the regiochemistry is the same for hydration. You'll add your hydrogen to the carbon that already has most hydrogen. In this case, it doesn't matter. So added a hydrogen to this carbon here, and then a positive charge formed on the other doubly bonded carbon, okay? Then this water that came off here, this is now a nucleophile, will attack the carbon with the positive charge here, okay? Which will form this product here, okay, which is almost our alcohol. We're almost done, but this is still OH2, okay? And that is not stable because that oxygen has one too many bonds. So one of these hydrogens will come off. You don't have to do anything to it. It will just come off spontaneously. And then you form your alcohol, okay? So it's just a tiny bit more steps, but it's the same general mechanism, okay? Does that make sense? Okay.
Why do you have a positive charge on hydrogen? Because it came off of the OH
Where?
when it's a leaving group, the hydrogen.
Yeah, so the hydrogen comes off as a proton.
Okay,
Does that make sense? Because you added it on as a proton, it comes off as a proton, okay? Because this leaving, this minus H+, remember how we used?
I was just writing it as an anion and not a proton.
Yeah, that just means minus that we're losing that hydrogen,
Yeah.
okay? So we use acid as a catalyst, so we have to reform our acid, okay? And the only part of the acid we used was the proton H+, so we have to reform that,
Right.
okay? Okay. So I don't think this will be a super hot topic on your test. You might have one or two questions about it, but I'll just go over it for.
I'm glad you're doing this because I've forgotten how to do the alkynes.
Yeah, it's not. It won't. I don't think it'll be. It certainly won't be a major topic on your test. It might come up, but okay. So just like you can add water to an alkene, you can also add water to an alkyne, which has a triple bond. And again, it also has to be acid catalyzed. Okay, and then you form a ketone. If you remember, a ketone has this C double bond to O group, and then you have alkyl groups on either side. Okay. So the mechanism for this, again, you have to make this hydronium. Okay. for this bond to break. So the arrow will go from the triple bond this time to the hydrogen. This OH bond will break, whose bonding electrons will go to that positively charged oxygen, which will reform water here. Okay, so again, same thing, hydrogen will add to the carbon that already has the most hydrogen. Okay, which I will add to this one. So now I have CH2. I still have a double bond here because I only broke one of those bonds. Okay, but now I have a positive charge on this other carbon. So this water, I'll use a pointer, this water that I formed here, okay, will attack on the positively charged carbon, okay, to give this product, okay, but we know that's not stable because that oxygen is positively charged, it has one too many bonds. So again, we'll lose this hydrogen easily, spontaneously, you don't have to do anything to it. Okay, so when that hydrogen comes off, you just have an OH group here. And this highlighted group right here, this is called an enol. It's a tautomer of a ketone, which just means that they're isomers that only differ by a hydrogen. Okay, so this, so an enol, you have an oxygen bonded to a carbon that's doubly bonded. And this will enhance the nucleophilicity of this double bond because these lone pairs of electrons from oxygen can come down to push those electrons over. So that will enhance the nucleophilicity of the double bond. Okay. So once we form our enol, we'll use another molecule of hydronium. These bonding or these lone pair of electrons from the oxygen will go here to form a double bond between the carbon and the oxygen, which will push these electrons over to the hydrogen, which will break that OH bond again. Okay, so we formed a double bond here, which formed a positive charge on an oxygen again because we have one too many bonds on it. And then we added this hydrogen here. Okay, so again, we add the hydrogen to the carbon that already has the most hydrogens, so it'd be this one. Okay, almost done. Again, this oxygen has that positive charge because it has one too many bonds, so that hydrogen will come off easily. You don't have to do anything to it. And that would be our product. It's our ketone. Does that make sense? Like I said, I don't think that will be a major topic in your test. But it is still good to know.
You are recording this, right?
Mm-hmm.
I mean, we'll have to go back and listen to that again. I think one of the questions in our homework assignment is we have to, it's kind of like the reverse reaction of that. The product has to be an alkyne.
Mm-hmm.
So I'll have to study that.
So, okay, so you're given a ketone and it's asking for an alkyne.
Yeah, it tells you what the alkyne is, and you have to figure out how to make it.
Okay. So, to my knowledge, you would just work backwards from this. Okay, so you would protonate the oxygen here to form this, and then I think, hold on.
You might just want to take a look at it.
Yeah, I think you would just do pretty much the exact same thing but backwards.
Okay.
Or is it it's just asking you what, okay. Is it asking you for the ketone or is it asking you for the alkyne?
The specific question.
Show reagents and experimental conditions to synthesize the following compounds from one propanol. Any derivative of one propanol prepared in one part of the problem may be used for synthesis of another part of the problem.
And it's H, it's propane.
From propanol?
Yeah.
Okay.
But you can actually use like another part of the problem, like in the previous things, and start from there, I think, and work.
Okay, if you start with an alcohol,
So I think
I don't know.
We can probably start with 2-propanol to get propine.
So,
That would be the easiest way, I would think.
I don't know.
Okay, well,
Yeah, that's what I remember. I think I remember that one from last year, and I just don't remember how I did it. He wouldn't ever ask you to do that, I don't think. Yeah, I think I remember that from last year. To me, the homework, in my opinion, was always harder than the test. So, don't get too hung up.
last semester, but this semester, I think it is.
I
don't know,
always
haven't
thought
had
it was
a test
harder.
this semester.
So don't get too hung up on the homework. Okay. So last few things. Then about epoxides, which are 3-membered rings where we have carbon to carbon to an oxygen, and we form a little small ring. And we make epoxides by oxidizing an alkene, and we normally use something called a per acid to oxidize. Okay, so that's just a carbon double bond to an oxygen to another oxygen. Okay, and the one that's in the notes that, let's see if I can draw this from memory, that we normally, it's very common, I believe it is this, or something that looks like that. So yeah, it's just your common oxidizing agent. It's a per acid. You don't need to know like a mechanism for this specific way to make an epoxide. But yeah, it just oxidizes to the 3-member ring. Okay, so epoxides are electrophiles, which is the important part. Okay, so we also learned about Grignard reagents. Grignard reagents are very important. This will definitely be a big topic on your test. So Grignard reagents are one of the few carbon nucleophiles that we have. So they're formed by inserting a magnesium in between a carbon halogen bond. Okay, and you do this just by reacting a haloalkane with magnesium. Okay, so that's shown here. Okay, so this carbon-bromine bond is polar, but bromine is more electronegative than carbon. Okay, so it'll pull the electrons towards bromine. Okay, which would make the carbon partially positively charged and the bromine partially negatively charged. Okay, but when we insert this magnesium in here, okay, magnesium is less electronegative than carbon. So carbon and that bond will be pulling the electrons towards carbon. So now this carbon will be partially negatively charged and the magnesium will be partially positively charged. Okay, so that's why this is a carbon nucleophile, which just means that the nucleophilic center is on a carbon. Another carbon nucleophile is like cyanide. Okay, so because Grignard reagents are nucleophiles, they can react with electrophiles. Epoxides are electrophiles. So here's a reaction of a Grignard reagent with an epoxide. This carbon-magnesium bond is where your electrons will come from. So they'll go from that to one of the carbons in the epoxide ring, okay? And then that carbon-oxygen bond will let go, okay? So these two carbons will add to this carbon here. So this carbon is this one, these two are these two are these two here. And then this oxygen lets go and it's still connected to this carbon here, okay? And now, so carbon-magnesium is a covalent bond, but oxygen and magnesium is an ionic bond. So now these are ions, okay? So once we get here, since these are ions, we can just wash them off, Okay, so that's why we use workup, or it's like a dilute acid, and that's to wash off these ions. Okay, so most of the time, anytime you use metals in organic lab, you'll have to work up to wash off those ions. Okay, so when you do that, you also protonate that that oxygen to form the OH group here. Okay, so this makes an alcohol. Following me?
Yeah. Yeah, I'll have to listen to your lecture on this part again.
Okay. Last thing, this is what we've been doing the past few days, is hydroboration. Okay, so this is a reaction of alkene and diborane to form an alcohol. If there's one thing you learn throughout this entire course, I hope it is how to make an alcohol, because we've learned like 8 ways by now. There's lots of different ways to make an alcohol. This is another one. We react an alkene with diborane, which splits apart into 2 molecules of borane, which is BH3. A hydrogen from borane, I'll write that down. Okay, so this is borane. A hydrogen from borane adds to 1 carbon, and then the BH2 adds to another carbon. Okay, but we don't ever want this. I guess you could want this, but normally no one ever wants this. So we oxidize, okay, to replace that BH2 with an OH group, okay, which we normally, in this case, we normally do that with hydrogen peroxide, H2O2 in a base, so like sodium hydroxide. Okay, so the mechanism here, you remember the whole, this is a concerted anti-Markovnikov syn addition. Okay, so in this case, the hydrogen does not add to the carbon that already has the most hydrogen. Okay, because this does not proceed via carbocation. Okay, so again, Markovnikov's rule is all based on carbocations. We don't have carbocations here, so that rule does not apply. Okay, so instead, the hydrogen will add to the most substituted carbon, so the one with the least amount of hydrogens, okay, which will avoid steric hindrance, okay, because like these 2 groups here are a little bulky, okay, so if I try to add this BH2 over here, there'd be more steric hindrance, okay, but because this side, this carbon, is less busy, the bigger BH2 will want to add to that carbon instead. Does that make sense?
It adds, the BH2 adds to the carbon with more hydrogens.
Mm-hmm. Yeah, so it's just the complete opposite of Markovnikov. Okay, so the mechanism, again, arrow comes from the double bond to the borane, or to the B, and then this BH bond will break. These bonding electrons will go back to the other carbon. Okay, so that will add the BH2 to this carbon here, and then the hydrogen to this one. Okay, so again, we don't want this BH2 here, so we're going to oxidize with hydrogen peroxide in a base, which will form our alcohol. Okay, so again, main point, you want to remember that's the concerted anti-Markovnikov syn addition. Okay, so, and syn addition means that it's adding on the same side of the double bond. Okay, instead of like in the bromation of alkenes, which I didn't include in this because it wasn't on the study guide. I don't know if that will be on your test or not, but that's the one where one of the bromines add to one side and the other one adds to the other side. We remember that, where it forms like the triangle thing.
Yes.
Good. Yeah, it's that.
Anti-addition.
Yeah, right. So this is the opposite. It's syn addition, so both groups add to the same side rather than opposite sides. Okay. Any questions? If you need help on homework, I can help you with that now.